I thought I'd um, talk a little bit about complexity science and what football can teach us about complexity science. So any of you who know my research, and I know that Guy does know this very well, my research before I started becoming interested in football, which I'm going to talk about in a bit, it was all about collective animal behavior and various forms of how animals behave in groups. And there's a wide variety of species here. You've got ant trails, fish schools being frightened. You've got other fish decision-making situations. We looked at sheep and sheepdog interactions. We even studied how people applaud at the end of seminars. Whoops, I thought there was a video of that one. We did some work on crowd safety, as many of these examples are. We did studies replicating Stanley Milgram's looking up experiments. We looked at locusts, another ant trail, pigeon homing flight. And this is one of my favorites. This was when we studied prawns swimming around in the bottom of a bucket in order to look at the rules of interaction of them. And so what I was interested in and worked on for a very long time was the collective behavior of groups and how we could create mathematical models which allowed us to understand that type of collective behavior. Now, a few years ago, now it's almost sort of 6 or 7 years ago, I wanted to write a popular science book where I explained all of these wonderful emergent patterns that came out of animal behavior. And I wrote to various agents, literary agents and publishers, and I'd written one little example on football, and they said, well, much more interesting for the general reader than any of these animal things. No one's interested in animals, they told me, but everybody's interested in football. And so why can't you write about football instead? And so I ended up doing this. I am interested in football, so it wasn't a sort of torture for me to have to do this, but I ended up thinking about ways in which we could use this type of collective animal behavior research to understand lots of different aspects of the game. And the result of that was the book that came out now 6 years ago, Soccermatics, which is an attempt to model lots and lots of different aspects of the game using maths. And I definitely look at the collective motion of the players. I look at passing networks, for example. I use network science in it. I look at game theory about if you should try to go for 3 points for a win. I look at all different ways in which you can understand football using mathematics. And in a way, when I first did this, it was really that and the book, for those of you who are interested, I know many of you are interested in human and animal social behavior. The book is 2/5 this type of research, and it's 3/5 examples from football. So I kept a lot of the original research ideas in it. But it ended up taking me on this most incredible journey, because when I started talking about this, I got more and more invites from clubs and from national organizations to talk to them about how they could use mathematics to really understand the game and win matches. And I ended up going down to Barcelona. I was asked by a TV company if I could look at the mathematics of Lionel Messi. And so I went down to study Messi in firsthand, and I met all their data scientists who work down there. I now work with the English FA on a project. I work with Ajax. I work professionally with a Premier League club. And I also, I'm going to come to this a bit, I got to work very closely with my, local club. They're not my really local club in Uppsala, but my local club in Stockholm, to study, to help actually be with the team. And so this led me on an amazing adventure of my own. And I'm just going to give you a couple or, a few small insights into the type of modeling we use. And we use, of course, it all during the time from when I wrote Soccermatics, there's been this massive revolution in that we've got to all talk about machine learning now instead of statistics. And so I'm going to talk a little bit about machine learning that we use here. And one example of how you do machine learning in football is the following. You have the following problem. You want to evaluate a pass. So we're very interested, for example, in this pass that's been made here. How do we assign a value to it? And what we do is we create a model where we have lots and lots of, we look at all similar passes to it, and we look to see how often does a pass of this type lead to a goal. So this might be a sequence, this might be one attacking sequence by a team. This might be another attacking sequence. This is another attacking sequence. In one of them, it leads to a goal. In the others, it leads to the ball going out. And so we can find out how often particular types of passes lead to a goal, and we fit a logistic regression model, or we can use other machine learning tools to estimate the probability that a particular pass will lead to a shot. And then from there, the probability it will lead to a goal, given that there's a shot. And by multiplying these two probabilities, we can start to make a model which evaluates every pass in a football match. And this gives a kind of heat map of the value of a particular pass. So if you pass the ball from here to a place near to the goal, you're attacking this goal, then it's very valuable. So the hotter this area is, the more valuable the pass is. If you pass back, it's obviously less valuable. But what we're able to do is, for any pass and any action that a player does in a match, is assign a value to it. Here's an example where we've assigned values to the Swedish national team. They're playing in the World Cup this time, and Aslani, who's one of the top strikers, these are the, she's an attacking player. These are her passes which created the most danger. So you can see these types of passes straight forward into the box. They're the most valuable passes in football. And we can create an algorithm which then ranks the players. Aslani produced the most danger, Caroline Sager the second most. We can actually produce an algorithm which ranks the players. And this is used a lot in scouting. So now you can actually measure the danger created by each individual player. To illustrate an example of this, let's take where all the players' positions are. And I'm going to come back to that as a issue later on. So that's one way which we can model football. We can look at the value. Another thing that we can do is we can look at the geometry. And this is where we start to think of aspects of collective behavior. And I really enjoyed, this is a team that I worked very closely with. So I worked twice a week. I was visiting this club and I worked with the players on their play. The green team is the team that are our team, and they've just regained the ball. They're going to attack now. And this is going to have well, you can watch it now and see what happens. So we scored a very lovely goal in this occasion. And what we'd do, and we'd actually show these types of things to the players, is we could replay these games looking at the area we control of the box. And in that area, we control a lot of area outside the box. And then you see that this player number 20 opens up here. Number 40 is opening up down here. 23 is opening up and controlling a space here. And we're able to measure during the attacks which areas we control and which areas the opposition control. And what do I mean by control here? Well, this is just a model where we say who would get to the ball first if we drop the ball at random. So we make a model of the movement of the players. We say if the ball was dropped down there randomly, this player would get there first. And green areas where a green player, the Hammarby team, which I work with, would get there first. Blue areas are where the opposition would get to the ball first. Just to give two key points during this attack, when our defender headed away the ball, notice that we controlled a lot of the area around and outside the box. So you can think of a clearance as basically a ball just going in a random direction. And since we control this area, the ball ended up going to number 22, but since we control this area, we're much more likely to recover the ball. And then when we start the counterattack, when we started running in this direction, you see the ball is here now. You see player 20 opening up a space and player 40 opening up a space. And this is all, it's reasonably quantifiable. We can actually see the space creation of the players as they perform certain actions. This is another type of model. This is one where we, instead of just measuring space, we actually looked at the physics of the ball in order to understand what was a possible pass to be made. And this is in the attacking sequence right at the end of the video there. Number 20 has the ball and he passed wide to number 40, who then passed back. But you can actually see the probability of scoring in each of these particular situations. And we could say that if, sorry, not the probability of scoring, the probability of the pass being successful. And when he makes the pass, he's a 60% chance of making that pass, a 98% chance of making that pass, and he decides to make the more likely to succeed pass out to the other wing. And we use these tools. I mean, this was the fun bit about it, is we'd actually sit with the players and discuss these situations afterwards. Of course, this one ended very happily with a goal. It's not always the case. When they don't score, you want to analyze those situations too. But it was a very useful tool for the players to go through and talk about their own decision-making during the matches. This is another situation slightly later, where now there's a smaller chance of making this pass, but it's very likely to result in a goal if it's successful. And there's still a larger chance of making that further pass out there. And now, as well as working with the players, I got the opportunity to work very closely with the coaches, and we could actually come up with geometry-informed tactics for the matches. And this was one of my favorites. We came up with an idea called the cross. And the idea is very much like when we regain the ball. So in this case, we're the green team, we're attacking. In football, whenever you show it, attacking is always left to right. So we're attacking left to right. We have the ball down here. And what the players have done is they've formed a cross here, which occupies as much space as possible. So if we do lose the ball in attack, we can quickly regain the ball when it goes out. And this was something we did. This is the head coach of the women's team and the head coach of the men's team. Both of those teams adopted that structure in order to stop the ball going out. And it's a very easy, I mean, coming back to the animal behavior thing, you know, we talk about these simple rules creating a collective structure. It's a simple rule to explain to the players that they should try and form this cross, and then it manages to actually cover a lot of space and allow us to perform better. And in particular, this player here, I talked to about the fact that he wasn't in the cross. And so we told him he had to move more central, which allowed 6 to play where 8 was, and 8 to move forward and be part of the attack when they were attacking. So we could actually, again, we could give this feedback to individual players. Oh yeah, this is a similar example with a women's team, 7 to 17. 17 should be here. We want to have 2 players marking this player who's out here. Finally, anyone who's been following, who's interested in self-propelled particle models, this was a project we did together with Barcelona. And the most exciting thing I think I found out when I started talking to Barcelona about these types of things is that they use a self-propelled particle model with 3 zones in order to talk to the players about how they should position themselves. And they use a zonal model. I'll go to that. Yeah, I talked about the zonal model, so I'll talk to that first. They have 3. They have like what when we've talked about the self-propelled particle models of zones, we've talked about the repulsion zone. We normally talk about the nearest one. This is for Barcelona. This is called the intervention zone. If you've got the ball, you stay on the ball. If you've not got the ball and you're the nearest player of the opposing team, you get the ball. That's the rule that you apply in there. Then there's something called the mutual help zone. That's where you do runs to open up space to be passed. And near to the ball holder, you're in the mutual help zone. In the cooperation zone, that's more like I was talking about here. This would be a cooperation zone problem. Away from that, you organize in order to sort of keep a stable structure on the pitch. And so every player has to think about which zone they're in, and then they should base their behavior on the particular zone they're in. This is an illustration, again, of the running and the passing probability. You can see this is a run by one player who runs out in this direction, who opens up for the other player. So anyone who's maybe not so football trained might not have noticed so clearly that this player is doing the important run here, even though he doesn't receive the ball. He makes the run, which then opens up for the player who's wider out. And we'd actually compare and look to see we'd make models of how you should run, and we'd compare to see what the optimal strategy was compared to the real strategy. Now I've been just keeping time in the last session, and now I'm not sure that I'm keeping time on my own. So I'll come to my final question: what we can learn from football about complexity science, because what I like, I've changed my view of complexity science a bit, and I really like this image here. And the image here is like, these are the interacting individuals, and there's lots of things going in and out. And the point is, when we build a model, we can never fully capture any one part of the system. And that's exactly what I found when I was working with football. Like one day it would be these pitch control models, one day it would be evaluating actions, one day it would be looking at shooting, one day it would be simulating the league using a Poisson distribution. And all the time we'd have to change the angle and the way that we looked at the particular system. And I think that's the sort of take-home message for thinking about complex systems later, because I think that is a lot of the way that we should be thinking for modeling any complex system. And I certainly had to become, I mean, when you do something like modeling football, it's not kind of a outside academic activity. You sort of become part of the system you're studying. We became both parts of the men's and the women's team. And to say what this view is, so then I had this view, I mentioned this just before, that we're making models of predictions, we're making models of attacking runs, of biomechanics, all trying to get these different views of a complex system. And I've written a little bit about this, this whole idea of kind of open machine learning and looking at complex systems in this way in a paper with Abebe Birane, where we use football in order to illustrate this. And finally, as well as Abebe, I'd like to say thank you to Javier Fernandez at Barcelona for having me, Pablo Pinach Acra, and who's the Hammarby coach, and also Fran, who worked as the data scientist for Hammarby. So thank you very much.